Hi everyone, my name is Juana Tortua and I'm joined by my teammates Chikaha Suji and Harrison Sang to present to you today's SplatGrasp, our framework from language-guided 3D grasp affordance generation from 2D Gaussian splatting reconstruction. The idea behind SplatGrasp is to use a recent technique called 2D Gaussian splatting to reconstruct a high-quality mesh of an object from a casual smartphone video capture. We then combine this geometry with language-driven segmentation so that the robot can understand instructions like grasp the vase by the handle, not just stable grasps, but semantically meaningful ones. This is the overall pipeline. Starting from multi-view images, we use CallMap or any other structure from motion tool to get the camera poses. Then using these, we train a 2D Gaussian splatting representation of the object, which gives us detailed surface and accurate depth maps. With these depth maps and language segmentation masks produced by LangSim, a language-grounded variant of segment anything, we isolate the object and the specific subpart the user references. After TSDF fusion, we have a high-quality object mesh and a semantic affordance binary map defined on it. Finally, we run GraspNet, which integrates the affordances, proposes candidate grasps, and picks the one that best matches the user's language query. The result is a robot grasp that aligns both physically and semantically with what we want. Here's a quick video of the 2D Gaussian splatting output. Notice how we can smoothly rotate around the object and see the surface details clearly. We use 2DGS over 3DS, NURBS, or other reconstruction methods since it intrinsically represents surfaces with planar Gaussians, making the geometry reconstruction yielded by TSDF fusion cleaner and more accurate. The result is surprisingly high quality mesh assets. After applying LangSim masks with TSDF fusion, we get two mesh layers, one for the entire object and one for the subregion of interest. For example, the vase handle. By blending these two, we assign a binary affordance score to the vertices of the object mesh that will be used for grasp generation.
After recovering the mesh and semantic affordance field with TSDF, we can generate grasp candidates. A point cloud is constructed from the mesh vertices and input into GraspNet. Simultaneously, since the mesh and affordances are jointly reconstructed, we can create an affordance mapping from the semantic field by performing a one nearest neighbor search for each affordance point on the mesh vertices. Next, we apply NMS to filter redundant poses, ensuring a diverse set of candidates. Then compute a joint score by multiplying softmax probabilities with affordance scores, yielding the top K grasp configurations. First, we show the vanilla grasp generated by GraspNet in the absence of language guidance. Notice that the candidates attempt to grasp the underside or the sides of the object. However, these are infeasible maneuvers because the object is either too big or rests on a supporting surface. These issues stem partly from the complexities of absolute scale recovery from CallMap and the absence of semantic guidance. By contrast, our open vocabulary affordance generation, guided by language queries, relaxes the strict reliance on geometric feasibility alone. When the affordance scores are integrated, we consistently achieve more human-like, semantically meaningful grasp configurations.
We create a simulation environment using Drake to validate our approach. We construct a simulation environment using a KUKA EVA robot equipped with a WSG gripper. Objects are prepared by generating meshes from Gaussian splatting. These meshes are added with physical properties such as collision geometry and inertial parameters and converted into SDF for simulation in Drake. By using the BHA-CD method, we decompose objects into convex components for accurate collision modeling. Next, we perform motion planning to perform multi-stage pick-and-place manipulation. Each stage of the sequence, including pre-grasp, grasp, post-grasp, pre-place, place, and post-place, is carefully defined. Specifically, the grasp poses are informed by affordance scoring, ensuring affordable and stable interactions with objects. We solve inverse kinematics to compute the joint configurations required to achieve these poses. IK ensures the robot and the vector aligns with the target pose, considering constraints on position and orientation. Finally, a trajectory optimization module generates smooth, straight, and orientation-consistent paths between configurations. The optimization minimizes joint movement while maintaining alignment with the desired path.
We introduce SplatGrasp, combining 2D Gaussian splatting for view-consistent geometry and language-driven segmentation to achieve semantically meaningful grasps for complex multi-stage manipulation. This integration of geometric precision and open vocabulary language understanding paves the way for more intuitive and adaptive robotic manipulation.